Hello, this is Bruce Wagner, Solutions Consultant for CED Keithley Patterson in Arkansas. We are part of the CED Central Industrial Division, a group of Rockwell Automation Allen Bradley distributors. Today I'd like to present to you VFD cable and some relatively clear facts about VFD cable and its usage. There's been a lot of talk about VFD cable for several years since the release of IGBT output style PWM drives. A lot of this talk, though accurate about the issues, was sales noise, pun intended, until the NFPA 79 of 2018 was released. This presentation is to try to outline some of this data about VFD cables to help you choose the best product for your application. All the information should be used in conjunction with other very important documents, such as the drives IN 001, the book for Rockwell PWM VFD installs, or the drives AT003, an industry-focused application guide for Rockwell PWM VFD installs, along with specific product installation and or user manuals, such as the 750 IN001 for the PowerFlex 750 product and the 520 UM001 for the PowerFlex 5 products. So the first question becomes, is there a clear specification, standard, or NEC guide for VFD cable that we can point to for clarity in the situation? The answer has been no. And this has been a major issue for many years. Each manufacturer did what they thought was correct in the cable construction and called it VFD cable. This included using VNTC or vinyl nylon tray cable, which is essentially THHN insulated conductors under some jacket. And that construction came with or typically without shields. And secondly, if there's no clear spec standard, then what do we use for guidance? Well, the first part of the answer is NFPA 79, 2018, 4.4.2.8. It allows the use of 600-volt insulated cables to connect power conversion equipment, think servos and VFDs, as long as it is listed as a flexible motor lead cable with the proper type insulation. This spec requires thermoset insulation such as XLPE or EPR, cross-linked polyethylene or ethylene propylene rubber, such as RHH, RHW, RHW2, XHHW, XHHW2, etc., which also effectively means no loose THHN conductors also. The second part that we turn to for guidance is physics, which gets deeper about this. We're generalizing some of it in this presentation. And the third is the installation guidance from the manufacturers, such as the drives IN001 with the drives AT003. Now, this NFPA specification does not allow the use of THHN because it uses thermoplastic construction for insulation, which can deform and thin during the installation just from the physical stresses of the install. Deformation and thinning reduces isolation distance of the conductors, the wire, leg to leg, and leg to ground. Thermoplastic can soften with heat. This can be a high ambient in conjunction with the heat generated by the power passing through the conductors. Once it softens, the conductors can float inside the insulation and again cause deformation and isolation distance reductions. THHN is water resistant only if the nylon jacket remains completely intact in the water area. What this does, the nylon prevents the PVC from absorbing water, and this absorption of water in an already thin insulation wall can reduce the distances for isolation even further. And I dare you to find a typical installation where the nylon hasn't been damaged at some point during the install. THHN is mass produced as a building wire to have an effective price point. It has a high probability that the conductor can be eccentric inside of the insulation, although they try to maintain 19 mils of insulation around the complete conductor. It can be less on one side, more on the other. It is an inexpensive cable with the thinnest insulation thickness in general and has low conductor separation values that play into the physics part of this. There is a high strand factor on the wires itself inside the conductor, and that plays into the calculations in physics. And then it has a high dielectric constant, which gets into some of those physics issues even further, as we will show in a few more slides. Now, the thin insulation combined with the high strand and insulation dielectric factor causes issues. There can be high charging currents that can trip small drives at shorter motor lead distances. Things like instantaneous hardware overcurrent fault, just turning the motor on and turning the drive to run. Thinner insulation can share more power with other wires in a raceway. It may not run the motor, especially at longer distances of motor lead lengths. This is called capacitive coupling, and the power that's in this conductor that has more power on it is shared with the one next to it that has less power on it. Cable failures become more likely, especially if water is present. Damaged nylon lets PVC absorb water, shortens leg to leg, leg to ground distance, and insulation failures caused from a term called cable treeing or insulation blowout become common. The thin insulation is also prone to failure under the peak voltage spikes created by the drive output PWM waveform. And noise can run rampant in a circuit. This noise is uncontrolled because it's not under a shield, doesn't have a low impedance path back to the source, the drive. And these things cause motor bearing failures, communication and network issues, analog loop issues, etc. So THHN still doesn't cut it from the physics, because what cable construction affects cable charging current? Generalized, it's a surge impedance of the cable or V bus divided by ZO. Surge impedance is found from the cable inductance, cable capacitance, or this calculation. Therefore, cable capacitance calculated from the separation distance of insulation thickness, conductor to conductor, and conductor to shield has a major influence on cable charging currents. Below is the formula, courtesy of Rockwell Automation, Allen Bradley Drives Division. So as you can see from this formula, these are the places where the stranding factor, the insulation dielectric constant, etc., start coming into play versus the physical spacing of the conductors itself in the cable. So this picture depicts the insulation thickness, showing the best VFD cables at 40 mils or 0.04 inch thickness between the conductor, or on the outside of the conductor or greater. This gives you 80 mils separation. Good at 30 mils, and not recommended at 19 mils, which is THHN. It also shows the separation of the conductors from the shield, because this same distance separating wire to wire separates wire to shield. And all these things factor into cable charging currents, noise propagation, etc. All those physics issues that we get into when we discuss VFD cable. So why use VFD cable, especially shielded versions? Well, it can help minimize downtime from cable failures, especially where there's water in the area. And this doesn't just have to be food processing. A lot of people think when you say water, you're talking food processing. No, any install where the raceway transition humid areas or is underground can have standing water in the raceway. That standing water can be absorbed by the PVC and THHN if the nylon is damaged. You can avoid nuisance drive tripping from cable charging and shared current issues, which is even worse with loose THHN wires, because you have no idea in the raceway where they are in relation to the other wires. You can help avoid noise issues that are hard to troubleshoot, controller communication issues, erroneous analog loops, companion drives tripping for no apparent reason. You can reduce motor bearing failures from noise by having a better path back to the drive, which is the source, than the motor shaft and machine steel. Look up AC motor bearing fluting for kind of a treatise on what this situation is if you haven't already experienced it. And safety. Shielded VFD cable minimizes power sharing between cables, reduces the likelihood that a LOTO, locked out tag out device, having power on its wires from the neighbors in the raceway that have power up on them and are sharing it with the open conductor. So in VFD cable construction, effectively there are 3 levels, in my opinion: good, better, and best. All use some type of thermal set insulation, less prone to physical issues than the THHN, and it also supports the tray cable rating on the conductor. All use some kind of outer jacket, usually some version of TPE or thermoplastic elastomer rubber, which also supports the tray cable rating. All use tape and/or braid shielding. I prefer tape and braid. Highest coverage level with the lowest impedance path for the noise to return to the source, the drive. They all have at least 50% or greater rated grounding conductors. Ground coverage of less than 50% in a VFD cable can contribute to multiple issues, including control of noise or lack of control of noise. Large cables, manufacturer dependent, are what we call symmetrical, which have 3 ground wires in the interstices between the power conductors. Because of their physical construction and the technical design, those 3 ground wires perform the function of giving us the equivalent ground rating we need in order for noise control and to ground the equipment. Typically, a VFD cable will use advanced assembly methods to control conductor lay, inside insulation, and jacket. Conductor lay or controlled orientation is critical to reducing cable charging currents along with noise cancellation between the conductors of the PWM waveform to the motor and reduction of overall cable diameter. And all are typically thicker insulations which are more resistant to the reflected wave spikes caused by the drive PWM output. In the VFD construction, how to choose a good VFD cable, what I call good cable may be a reduced thickness wall on the insulation, but it is 30 mils or greater size dependent. May have a reduced thickness on the jacket, but sufficient for the application. It is flexible, usually has about a 7.5 times bend radii for installation. Since there is no bend radii listed typically for these cables for full flexing, that means they can't not be flexed all the time. Usually because of the construction, they meet Class 1 Div 2 per Article 501 of the NEC. And in most cases, they're tested at 2,000 volts for resistant to reflective wave spikes from the drive output. The limitations with the good cable construction may be your motor lead lengths are reduced as much as 32% or to about 68% total of the drive's IN001 Appendix A motor lead lengths because of cable charging current limitations, especially on the small drives. The 600 volt rated insulation with the 1000 volt rating for power conversion equipment means that it is a better cable than THHN. But once again, at the 1000 volt rating, you now get into some issues that after the reflected wave gets so far, it can still cause other issues. May have an overall outer diameter larger than the better class cables. And you do have some limitations on the number of cables per raceway that are bundled together, approximately 10. This is to help control noise, cable power sharing, etc. In the better construction, has a reduced cable diameter and weight compared to other VFD class cables because of advances in technology being implemented in the construction of the cable. Usually it will have about a 24 mil thick wall, but it will be greater, cable size dependent. Usually it is a special insulation formula and a better conductor wire design stranding factor to offset the thinner insulation. Usually they have an advanced TPE jacket with a reduced thickness. You will see these cables have a 7.5 times bend radii for installation, and then a 15 times bend radii for continuous flex install. So now, if you keep that bend to 15 times or greater in the curve, this cable can be used in a continuous flexing application. Because of construction, it again will meet Class 1 Div 2 per NEC Article 501. Usually these cables are tested at 3,000 to 4,000 volts, size dependent, for an improved resistance to reflected wave spikes from the V-drive PWM output. Some limitations with the better cable are motor lead lengths reduced to about 80–85% of the drive's IN001 Appendix A cable lead length distances. Again, because of cable charging current limitations, especially on small drives. And the max motor lengths, regardless of size, may be limited to 175 feet to 200 feet after the above offset. Now, once again, a good point is a 600 volt rated installation with a 1,000 volt rating for power conversion equipment, but that again puts a limit on the number of cables per raceway. So for 11 to 14 amp drives output or smaller, you're limited to about 10 cables max in a bundle. For 17 amps and greater drives, you're limited to 6 cables in a bundle or raceway. And if you mix large and small drives, 17 and above or 14 and less, then your limitation is 6 cables because of the smaller cables. The best VFD insulation construction usually has a conductor insulation thickness of 40 mils and greater, even on the small wires. It also has an advanced design TPE jacket, but usually because of the thicker insulation and thicker jackets, excuse me, the flexible rating is 7.5 times bend for installation only, and they don't usually carry a full flex rating. They do meet Class 1 Div 2 per Article 501 of the NEC, and they are tested at as much as 6,000 volts for maximum resistance to reflected wave spikes from the drive PWM output. Limitations: at 12 gauge size, no reduction in lengths in drive's IN001 Appendix A cable lead length restrictions. 12 gauge is a size tested by Rockwell Automation Allen Bradley in the drives division for their certification, even on the small drives. The max motor lengths typically get limited by NEC and NEMA voltage drop only, i.e. if you're within the drive's IN001 limitation, then you start looking at voltage drop at that distance to make sure that you maintain enough NEC NEMA voltage on the motor for full torque. If you need further technical assistance in determining whether this works or not, Rockwell has a site to calculate. It's located at https://rockwell.transsim.com. Now, you will register with an email, but you won't be getting any spam. And effectively, this site is running on a supercomputer that's been maintained by interns in the drives division and allows you to do multiple calculations. It's an excellent site, so I would suggest taking a look at this. The cable comes with a 600 volt, 2000 volt TC rating with 1000 volt rating for power conversion equipment, but with a 2000 volt or greater capable insulation and tested at 6, it is less influenced by the spikes from the PWM output of the drive. Typically, the limit on the number of cables per raceway is based on raceway size, cable fill capacity, load bearing weight of the install, and those other physical factors. So where do I install a quality VFD cable, and what questions do I ask about it? Well, any place the site uses VFDs or power conversion equipment, such as solar farms, DC drives, battery chargers, etc. And questions I've drilled down to in my install and application are, do I use the power conversion equipment such as above. Am I having any issues with the install? And if so, what are they? They may be pertinent even if you don't think it's conversion equipment cable related. How long are the lead lengths? Again, we have to look at that physics to see how far we can go. If I do use VFD cable and I'm having issues, what is the construction of the cable I'm using already? Could it be that I need a thicker insulation or better shielding, something of that nature? And how can I use the proper VFD cable to increase safety and reduce downtime? Well, separation of the conductors, less shared power, less issues with water in the install. And now that I've decided I'm using VFD cable, which has shields and things of that nature, are there any cable accessories to make my install easier? And the answer to that is yes, we can provide such accessories. Here's a couple. Typical VFD cable accessories to include are cable connectors and glands with proper ground attachments for the shield to PE point at both drive and motor. Very critical. When you're dealing with shielded VFD cable on a drive to motor install, it is unlike analog signals where you only shield at the source end. Power shielding must be both ends, at the drive, at the motor, and the shield must land at the same point the ground conductor does to prevent noise propagation across the panel, through the metal, steel, etc. Also, we can have shielded grounding attachments like the Icotech or similar. You can use two of these on an install, one at the drive, one at the motor, to get a more proper install. On the left, we have a unit that is built for use with drives that has a grounding lug on it. You peel part of the insulation, or at the end after you come out of the cable connector, the cord grip, snap onto this, and now you can land a ground wire under the terminals of the drive on the PE where you landed the PE ground out of the VFD cable. The other option that we have is a fairly new one that was released, which is a fork tongue terminal, where you do the same thing on the shield as far as stripping insulation, but with the fork tongue, you can now slide that under the PE ground strap on the drive so that your shield ground and your PE ground are at the same place, but you're not landing two wires. You're still only landing one wire to make it more convenient. So this is some things about VFD cable and some accessories. Thank you for watching this. And if you have questions, contact your local drive specialist, distributor drive specialist, or Rockwell technical consultant, and they can provide further assistance and information regarding these items and their installation. Again, thank you for your time and have a good day.